Torchasarray. Description. The torchasarray function converts a NumPy array or a list to a p-torch tensor. It provides a convenient way to seamlessly integrate NumPy and p-torch. Inputs. Input 1, a NumPy array. This can be a multi-dimensional array. Input 2, a list. This can be a nested list representing a multi-dimensional array. Outputs. Output 1, a p-torch tensor. The data type of the tensor is automatically determined from the input array or list. Steps. Step 1, the function first checks the input type. It accepts either a NumPy array or a list. Step 2, if the input is a NumPy array, it creates a p-torch tensor with the same data and shape as the array. If the input is a list, it converts the list into a NumPy array and then creates a p-torch tensor from that array. Challenges and fixes. Challenge 1, data type mismatch. If the input NumPy array or list contains data types that are not directly supported by p-torch, a type error might occur. Sample use case that resulted in challenge 1, torchasarray 1. 2. 3. A. Fixes to challenge 1, convert all elements of the list to a compatible data type before calling torchasarray. Challenge 2, complex numbers. p-torch does not directly support complex numbers. If the input array or list contains complex numbers, the function might return a tensor with only the real part of the complex numbers. Sample use case that resulted in challenge 2, torchasarray 1, 2j. 3, 4j. Fixes to challenge 2, use torch complex to create a complex tensor from the real and imaginary parts of the complex numbers. Torch as tensor. Description. The torch as tensor function converts a given input to a p-torch tensor. This function operates in place, meaning it doesn't create a new tensor object, but rather modifies the existing one. If the input is already a tensor, as tensor returns the same tensor object. Inputs. Data. The input data to be converted into a tensor. This can be various types like lists, tuples, NumPy arrays, or other p-torch tensors. D-type optional. The desired data type for the tensor. If not specified, it defaults to the data type of the input. Device optional. The desired device for the tensor. If not specified, it defaults to the device of the current tensor or the default device if no tensor is present. Outputs. Tensor. A p-torch tensor containing the converted data. Steps. The function checks if the input is already a p-torch tensor. If it is a tensor, it returns the same tensor object. If it's not a tensor, the function creates a new tensor object using the input data, potentially adjusting its data type and device. Challenges and fixes. Challenge 1, inconsistency in data types. Sample use case, converting a list of floats to a tensor with an integer data type. Fixes. Ensure the input data type matches the desired D-type or explicitly cast it before conversion. Challenge 2, tensor memory location mismatch. Sample use case, converting a NumPy array to a tensor on a different device than the current default device. Fixes. Explicitly specify the target device using the device argument. Torch as tided. Description. The torch as tided function is a powerful tool in p-torch that allows you to create a new view of an existing tensor with a different stride and shape without copying the underlying data. This is particularly useful for advanced indexing, reshaping, and creating custom views of tensors. Inputs. Input 1, input tensor, the original tensor whose data will be used to create the strided view. Input 2, size tuple, a tuple specifying the desired shape of the new strided view. Input 3 stride tuple, a tuple specifying the stride pattern for accessing elements from the original tensor. The stride specifies the number of elements to skip between consecutive elements along each dimension. Input 4 storage offset int. Optional an offset into the storage of the original tensor. Defaults to 0. Outputs. Output 1 output tensor, a new strided view of the original tensor with the specified shape in stride. Steps. Step 1, the torch astided function takes the original tensor input and the desired shape size as input. Step 2, the stride tuple defines how elements are accessed from the original tensor to form the new view. It specifies the number of elements to skip between consecutive elements in each dimension. Step 3, the storage offset argument is optional and specifies the starting offset within the storage of the original tensor. It's often used to create views that start at a specific element. Challenges and fixes. Challenge 1, out of bounds access. Sample use case that resulted in challenge 1, accessing elements beyond the bounds of the original tensor due to incorrect stride values. Fixes to challenge 1. Carefully define the stride values to avoid accessing memory outside the original tensors. Boundaries. Verify that the stride pattern is consistent with the dimensions of the original tensor. Challenge 2, aliasing. Sample use case that resulted in challenge 2, modifying the new view may unintentionally affect the original tensor because they share the same underlying data. Fixes to challenge 2. If you need to ensure that modifications to the new view don't impact the original tensor, consider creating a copy of the original tensor before applying torch astided. Use clone on the original tensor before applying torch astided if you need an independent copy. Challenge 3, memory overlap. Sample use case that resulted in challenge 3, defining a stride pattern that results in memory overlap between different elements of the new view. This can lead to unexpected behavior and potential data corruption. Fixes to challenge 3. Avoid specifying stride values that create memory overlap. Ensure that the stride pattern allows for distinct elements in the new view to access distinct memory locations in the original tensor. Challenge 4, performance considerations. Sample use case that resulted in challenge 4, unnecessarily using torch astided for operations that can be efficiently performed using built-in ptorch functions. Fixes to challenge 4. Consider using built-in ptorch functions like torch reshape, torch transpose, and torch permute for common reshaping and view operations whenever possible, as these are often optimized for performance. Torch astided is best reserved for more complex custom view manipulations or scenarios where you need fine-grained control over data access.